Okay. Here we are again, take two. Colorado, Genevieve's mom, excellent. I like that. Right? No last names, excellent. Very intimidating, excellent. God bless chemistry. And we're here today to talk to maybe kind of plug some holes. Kinga, you like that? Plug some holes? Yeah? Okay, how do you say plug some holes in Polish? She's thinking. Just a second. Yes? What is it? The same? Plug some holes? Can you like speak more loudly or? She's talking like this. I can't hear her. I'm an old man. I'm deaf. Yes? It sounds like something like that. Whatever. I don't know. I'm sorry. All right. I get some Polish email saying you're butchering my language, and I'll say, sorry, I don't speak Polish. So anyway, 3 rules that are important to study. Correct? There is the Aufbau rule. What's the Aufbau rule say? Anybody? Genevieve? Daughter of a chemical engineer who's sitting there drifting off into space like you're on a bus to Atlanta, Georgia from New York City?
So the Aufbau principle is basically electrons will occupy low energy orbitals before they will occupy high energy.
Yeah, I like that. That was well said. You put that in your own words. That's like brilliant. I like that. It said, that was better than I could do. I'm very impressed. It says that you fill lowest energy to highest energy. Now, every sub-level, you have a principal quantum number, correct? Then you have sub-levels, S, P, D, F, correct? Now, making up a sub-level are these little tiny spheres we call orbitals, okay? Now, the electrons fill from the low orbitals to the high orbitals, correct? High energy, right? Now, the second part of the Aufbau rule is what? That they're very sleepy today. What is it, Mohammed? Are you with me today there, big guy? You all right?
Yeah.
You're a little tired, huh? Okay, that's all right. It's Thursday, the end of the week. Anybody? We just said it. Yeah, Simon. Okay, I think I heard what he said. Yeah, the orbitals that make up a sublevel, these little circles, guys, these are all the same energy level in that particular sublevel. So it says that the orbitals that make up the sublevel are all of equal energy. So obviously with S it doesn't matter, but with P and D it does matter, and F. You see that? Okay. What's the next rule that we're going to talk about here? What's the next one? Yeah, Pauli's exclusion principle is actually very simple. Pauli's exclusion principle talks about strictly, absolutely only the orbital that makes up the sublevel. Some people say, like maybe it's old school, they say suborbital and orbitals and things like that. When they're actually referring to principal quantum number, they'll say the orbital, and then they'll say, when you have the sublevel, they'll say the suborbital. But that's not correct. The principal quantum number is the principal quantum number. Yeah, electrons orbit in that quantum number. Okay, fair enough. But the word orbital is strictly, solely, specifically, only the little sphere. And Pauli's exclusion principle says this, that those spheres can only contain 2 electrons, and those electrons must have opposite spin. And we assign the spin plus 1/2 and minus 1/2. So you have only 2 electrons. If 1 electron is in there, it has a spin, obviously. And then if there's 2 electrons in there, the second electron has to have the opposite spin. And we denote that by arrows, up and down. Yes? And then the electrons are assigned plus 1/2 and minus 1/2 relative to the quantum numbers, okay? But we've done all that. We're kind of reviewing a little bit. Okay, the next one says what? What's the next rule? It's actually kind of cool. Yeah, Hund's rule is going to be very important when we get to things like atomic radius, ionic radius, ionization energy. Because what you're going to look at when you fill, let's say we have a p orbital, a p sublevel made of 3 orbitals. So how many electrons can I fit into p? They know the answer to this, but they're like, not here. How many electrons can go into p? 6. Would you say 2?
I thought you said S.
He thought I said S. Did I clearly say P? Maybe I said S. You tell me at home. Okay. That's Kamal. He's a great guy. He's a little sleepy today. His eyes are like, okay. So, it's 6, right? But how do you fill them? That's what Hund's rule talks about. And the way you fill them is this. You fill, first of all, these are all at the same energy level. These are just frames from a picture. They're all the same energy level. This is not energy increase or decrease. I'm just saying what this looks like after each successive electron is put in, right? These are all the same energy level. You get that? Don't be confused with that. This is all P. 3P, 2P, whatever. It's just P. So it fills them halfway, and then it goes back and fills them completely. Now, let me ask you this. Let's talk about simply energy, okay? All right? If I wanted to remove an electron, we're kind of like going to the next chapter just for a minute in time, all right? I want to see what you think about something. We're not really going to talk about it, but I want you to think intuitively. What do you think? Not what you know. What do you kind of like? How do you feel about it? You ready? You ready? You ready? Now, this is the situation. The electrons are in the little orbitals. They're there. Okay? In each frame, they're there. And I want to know how much energy it's going to take to remove individual electrons given the situation that they're in, okay? All right? Yes? Okay. That electron I can remove, fair enough, right? But do you understand, what's easier to remove? This electron here or that red electron there? What would be almost easier? What do you think? What do you think? Removing this electron, that red one, or removing that one? What do you think would be more energetic? In other words, would require more energy. What do you think intuitively? I'm not asking you what you know. What you know is what you know. What you think in this particular point in time, I want you to think about what I just said, given everything you know. The hint is, you really know, you know the answer. They're just sitting there like stunned. But it's like the dead parrot sketch. The parrot isn't dead, it's stunned. One of my favorite sketches. You know what I'm talking about? Monty Python. It's great. Look it up. It's wonderful. They're stunned. Yes, Mountis.
They require the same amount of energy.
Same amount of energy? Okay. What do you think, Genevieve?
I would think it would be the black one because with the red one, that whole p orbital.
So the red one would be harder to remove, easier to remove than the black one.
The black one would be easier to remove because up there, the red one, that part of the p orbital is neutralized, it's filled.
Okay.
With the other one, it still is lacking the other.
Okay. So Mountis says that they're equal. Genevieve says it's easier to remove the red. Easier to remove it or harder to remove it?
Harder.
It's harder to remove the red one. Anybody else have an idea? What do you think? Everybody has an idea. It may not be right, it may not be wrong, but somebody say something. Eva, what do you think?
I agree with Genevieve.
You agree with Genevieve. Is there anybody who disagrees with Mountis and Genevieve? I'll give you a hint. They're both incorrect, but that's okay. I'm just wondering what you think. You see, the half-filled sublevel is extremely stable. It's unbelievably stable. And when we talk about something called hybridization, we kind of talked a little bit about hybridization yesterday when we talked about, or the day before when we talked about chromium and iron. Remember that? Remember? We talked about chromium and iron. Yes? You remember what happened? What did the chromium do? Do you remember? Was it chromium and iron?
I believe it was chromium and copper.
Chromium and copper. My apologies. Chromium and copper. Do you remember what happened with chromium and copper? I'm looking for the thing myself. There it is. It's on page 137. Excuse me for a second. Yeah, look at chromium. Look at page 136. What does chromium quite naturally do? What does chromium quite naturally do? Doesn't it take the 4s, one of the 4s electrons, to complete a half-filled D sublevel, doesn't it? So the short form for chromium would be argon, in parentheses, in brackets, right? And it would be 4s1, 3d5, right? Do that at home with the orbitals. Do that. Do you get it? You understand? So do you understand that urn, it reduces the energy a lot of the atom. It's very naturally occurring. The half-filled shell is very attractive. So this electron would actually be easier to remove than this one, because if I remove that one, I have a half-filled state. Very attractive. The next very attractive state is the complete filled shell. That would be a noble gas, right? Wouldn't that be a noble gas? The filled P, right? Isn't the noble gas very stable? Very stable? Yes? What group of elements are going to be these elements right here with the half-filled P? What group of elements? Give me a few elements. It's one of the groups. It's not 1, it's not 2, because that's S. It's not aluminum, is it? So what are the group? What's the family? It's group 15? And what is that group? What is that group? Name me some elements. Nitrogen? What else? No.
Nitrogen, phosphorus.
Nitrogen, phosphorus. Nitrogen, phosphorus. Arsenic. Okay. Now let me ask you a question. Does that mean those elements are stable because they're half filled?
No.
Or do they have very convenient bonding sites so that they might react a lot? These are questions we're going to ask later on in the coming chapters. We're going to start to put this stuff together. What does the half-filled shell do for the reactivity? Is it, let me ask you a question. Is this half-filled P shell, remember the valence electrons are where? What two sublevels? Valence electrons are only in the S and P, right? Yes? Yes, only S and P, correct? Those are the valence electrons. So what does this situation do? A half-filled state, it opens up 3 convenient bonding sites, doesn't it? Yes? So let me ask you a question. Does that create a very quick pathway to become more stable, maybe?
Yeah.
Maybe, yeah. So now we have to look at the covalent compounds that can be formed. Look at the covalent compounds that can be formed with nitrogen. Nitrates, phosphates, aren't those stable? Yeah, they're pretty stable under certain conditions. So these are questions, these are things we're going to look at. That's why we're doing this, so that the chemical reactivity will make more sense. Do you get it? So what does Hund's rule say? Hund's rule says that the orbitals are filled in this pattern. See that? Half filled and then all filled. And why does it do that? It does that for one reason and one reason only. And what's that reason? It starts with an E and it's not elephant. What's the reason? One reason. It does that. Starts with an E.
What does it end with?
5 letters. Oh, is it 6 letters?
Electron? Energy.
6 letters and energy.
Energy, yes. 5. Did I say 5 letters?
Yeah.
6 letters. Yeah, it does it because of energy. Neville, he liked that. Neville liked that. He liked that. He liked that. He liked that. I too am a little sleepy. Nah. You get it? Are we done? Now what we're going to do is we're going to plug some holes in the last section, which is, I've already done a couple of videos on this. This is on atomic emission spectra and the quantum mechanical model. Okay? Be right back.